So let's get started. Welcome to the first joint session of CAV 2020. It is my great pleasure to welcome David Dill for the first CAV keynote, where he's going to talk about formal verification of Libra blockchain smart contracts. I'm Shuvendu Lahiri from Microsoft Research and one of the co-chairs of CAV 2020. So it is my great pleasure to introduce David Dill. He is the lead researcher at Facebook, working on the Libra blockchain project. He is also the Donald Knuth Emeritus in the School of Engineering at the Stanford University, and he was on the faculty and the CS department from '87 up till 2017. David has had a very distinguished career and contributed to formal verification of software, hardware protocols, as well as voting technology and computational biology. He has received lots of awards, including a CAV award and an Alonzo Church Award. He is an IEEE Fellow, an ACM Fellow, member of National Academy of Engineering and the American Academy of Arts and Sciences. He has also received an EFF Pioneer Award for his work on voting technology, and is the founder of verifiedvoting.org. Personally, I fondly remember poring over the Birch and Dill paper on pipeline processor verification during my PhD, early days of PhD. And it's just one of the examples of how David's work in early CAV, that appeared in early CAV, influenced so many of us in this CAV community. So with that, I would like to welcome David. All the questions are going to be over Slack. I'm going to monitor them and post to David when David takes a pause. So with that, let's get started.
Thank you. I'm deeply honored to be giving a keynote at this conference. I actually attended the first CAV ever in France in 1989, when I had been less than 2 years out of my PhD program, and it was a transformative experience to me. At that time, there wasn't really a conference at the model checking, which was the main focus of it. And so it was a chance to meet the leading people in the field and make lasting collaborative contacts. So electronic conferences have their advantages, but I hope this COVID thing will be over soon. And I hope that I'll have a chance to meet more of you in person before too long. So I'm talking about a formal verifier for the Libra blockchain in the Move language. That's interesting. Okay, so I'm getting my computer to work. This is a project in the Novi division of Facebook with a group of talented researchers and software engineers who you can see here, some of whom are known to you, some of whom who will be known to you. We've got interns, we've got scientists at various levels of seniority at Novi who are all working on this project. So the Move Prover is a formal verification tool for so-called smart contracts on the Libra blockchain. So what I'm reporting is its current status, or its almost current status. This is a project that's really rapidly evolving, so I don't know what it will be like in a few months, hopefully significantly better, although it's performing reasonably well now. Just to orient you, I'm thinking about this as primarily an engineering project. I'm not going to be focusing on research results. It's about application of formal verification techniques in an area where people really care about getting results. The system is 100% open source, and you can go find it and see what we've done on GitHub. So the aspirations of the project are to allow complete specification of the functional properties of smart contracts. By aspirations, I mean things that may not be 100% achieved, but these are our goals. We want to enable fully automatic verification that implementations meet formal specifications, and we want to have specifications that allow for the fact that we want the system to allow for the fact that code is going to evolve. So we want to write specifications, and then when people make changes to the code, we want to re-verify those specifications to see if the code still meets them. We'd like something that runs interactively, just a little bit slower than a compiler. Sometimes it succeeds at that, sometimes it doesn't currently. And we'd like to be able to, we'd like to be able to re-verify after every change in the code. And so what I've learned in industry is we have this process of continuous integration where every time you check in your changes, a whole suite of tests get run before they're integrated into the main repository. And so we want to be able to run verification during that process. So I'll talk about some background on our organization and the blockchain. I'll talk about the move prover. I'll talk about specification, which turns out to be a major pragmatic issue for us. And I'll make some concluding remarks. So for background, what is Libra and what are Novi? You may have heard about this in the news. So Libra is a new global payment system and financial infrastructure. It's a blockchain that is intended to be infrastructure for the world, not controlled by Facebook. In fact, there is an association of different organizations, including for-profit companies and nonprofits, that are in charge of this blockchain, although currently Facebook has written most of the code. Novi is a digital wallet from Facebook that will support the Libra payment system. So Novi is one of many businesses that we hope will be built on top of the Libra blockchain. So the blockchain is the foundation for financial services on the network, and blockchains offer important advantages over traditional financial infrastructure, including distributed governance, open access, and security through cryptography. So for computer scientists, a lot of the banking system seems pretty archaic, and we want to update it and make it more accessible and less expensive. So it's been built from the bottom up, from the ground up, to prioritize scalability, security, and efficiency in storage and throughput, as well as adaptability for the future. So the Libra Association is specifically not run by Facebook. We went to great effort to make sure that we didn't control it because we wanted it to be infrastructure that's available for the world, where we could be one of many businesses. So you can see a list of the companies and other organizations that are members of the association here. I wanted to say a few words about Novi Research. We've got a research organization within the larger organization of Novi, and the reason for that is that blockchain technology is sufficiently advanced that we know that we're going to have to be doing research just in order to make our system work. And formal verification is a prime example of where we need to do that. So we have a number of senior and junior researchers. As a percentage of the staff on this project, it's relatively large. And the areas where we have researchers are in cryptography and privacy, formal methods for smart contracts, distributed algorithms, and critical systems code, and overcoming centralization barriers and consensus. So we have a number of researchers in distributed systems who are thinking about various aspects of blockchains. And system scalability and capacity, of course. We hope to be running a lot of transactions through this system. So the goals of the research are to impact the Novi organization. So we want to work closely with the development teams and the Facebook development community at large. We want to have substantial impact on Novi technology, which we already have had, in fact. And we want to be able to create differentiating technology that impacts Novi and Facebook. So there's a kind of a business need for the research organization. But like any good research organization, we're also aiming to impact the scientific fields that are involved. So that means publishing at top tier venues and engaging with the scientific community, building collaborations, for example, leading an independent research agenda and become a recognized leader in the relevant domain and okay, so I'll go back to the basics. A lot of you have heard about blockchains. Many of you may have done more work than I have, but blockchain is you know, a sequence of states, something we're all familiar with from temporal logic. And the states, the transitions from one state to another are transactions, essentially. So they're functions that transform the blockchain step by step, and then the blockchain is a temporal database of form. So transactions update the blockchain, and in blockchains that are based on smart contracts, such as our blockchain or the Ethereum blockchain, a smart contract is really just code that executes a transaction. At one point, smart contracts were thought to be more like legal contracts implemented in code, but I think the idea has kind of devolved or evolved into code that changes the state of the blockchain. In Libra, we're heavily relying on smart contracts. Like all of the core logic is in smart contracts. Transactions are atomic, so they either run to completion or they don't change the state at all. Okay, so the state of a blockchain state in Libra looks something like this. So it's kind of a tree where at the top level we have a large set of addresses, which are just numbers. And then each address has a set of types that can be published at that address. So in this case, I've got the type Libra account.t published there. Libra account is the module name, T is the type. This is something that has changed recently, but this is close enough. And then each type can have their records, or they can be records, and they can have fields. And so that makes a tree non-trivial. So a type such as Libra account can have a field called an authentication key, which is a vector of bytes, and another field called balance, which is going to be a type of Libra coin .t. The balance will have an actual number in it, which is the value of the balance of a particular account. And so you can store lots of other data at a particular address, but this is obviously crucial if you're going to have a payment system, the ability to maintain account balances for each address. So the idea is that each user would have one or more addresses. For now, the users are essentially financial institutions that maintain their own accounts, but the financial institutions have accounts on the blockchain, and those accounts obviously have balances, and there may be lots of other data stored there as well. In order to implement smart contracts, basically previous blockchains based on smart contracts, there are lots of them, but the original ones had some pretty bad problems with programming languages. So we thought it would be appropriate to design a special purpose language for the Libra blockchain. The language is called Move, and it's a programming language specifically for smart contracts. We designed it for safety, and so the previous languages in some cases were rather unsafe. For example, modules can only call modules that already exist. There are no reentrancy issues. So if you follow developments on the Ethereum blockchain, there have been some major bugs where millions and millions of dollars have been lost due to funny semantics of procedure calls. And Move's most novel feature is a special resource type that models physical assets that can't be lost or duplicated. So it's a record that can only be moved around and can only be created or deleted in the module that defines it. So Move has limited expressive power, something we all know in the formal methods community, but that is not necessarily understood in the rest of the world, is that there's an inherent conflict between expressiveness and the ability to reason about software or systems in general. And so Move is limited in its expressiveness to be safe, and that also makes it more tractable to do formal verification. So I'll talk a bit about the most novel feature of Move, which is the concept of a resource. So it's basically a struct, but you can't make copies of it. You can only create it and delete it and move it around, and the creation and deletion must be done by functions that are in the defining module of the resource type. So it's a so-called linear type. That's just a way of saying the points above. It's inspired by linear logic. Resource types we thought were an important thing to include in the language because it represents assets such as money or potentially physical assets. Blockchains have been used in the past for keeping track of various cars or titles to property or anything else. And so these are things that are not intended to be duplicated or only duplicated under controlled conditions. So that's built into the language semantics. Good. We also found some novel uses for these resources. So we're experimenting with the idea of using them to represent non-copyable capabilities for access control. And that's, you can actually go out there and look in the repository now and see a lot of the smart contracts that we've written in Move that are draft versions of the ones that we want to be running in the real system when it launches. So a blockchain is should be a high assurance system. I think we've discovered that the hard way because of losses in previous blockchains. So there are a lot of assets at stake, but of course that's true of lots of existing systems such as banking software. But the thing that's somewhat unique about blockchains is that it's costly to reverse a transaction. So on some blockchains such as Bitcoin, it's effectively impossible. And in fact, that's one of the, in the first paragraph of the Bitcoin paper, it mentions making transactions irreversible as one of the design goals. In blockchains such as Ethereum, reversing a transaction may involve doing a hard fork of the blockchain, and they have done that when required to do so, but it's costly in terms of hassle and reputation. So we don't like to reverse transactions on the blockchain. And a blockchain, of course, is out there on the internet, and it may be targeted by highly motivated and well-resourced adversaries. So the security challenges are more significant than some other software. So, and already we have an empirical track record where there may have been billions of dollars in losses, certainly hundreds of millions of dollars, because of bugs and vulnerabilities in smart contracts on blockchains. So our architectural strategy is that all changes to the blockchain have to go through Move and the Move virtual machine. That way, we're not searching around in the system to see what can change the blockchain. It's all in one place. It's all written in our programming language, which is especially designed to be secure and reliable. And we have a formal verification system where we hope to be able to formally verify every single program that can modify the blockchain state. So in particular, all changes to the store, that's the blockchain state, go through the VM. So imagine the store out there is this temporal database, it's the blockchain. There's a virtual machine that reads and writes to the store, and then that virtual machine responds to transaction requests, which ask for changes such as a payment from one entity to another on the blockchain. And those transactions may call functions that are in library modules that are accessible to the virtual machine. In fact, they are also stored in the blockchain. So all of the basic functionality in the Libra blockchain is implemented in smart contracts. For example, the basic implementation of the currencies, accounts, as I showed you earlier, validator lists. The Libra blockchain is maintained by consensus algorithms that have dozens of validators simultaneously keeping track of the states, so that, like most Byzantine consensus, there can be up to a third minus one of these validators can behave in a Byzantine fashion, and the blockchain will still continue to work. So for that to be secure, we have to have a set of trusted validators that we can access, and that information is stored and maintained on the blockchain as well. Okay, so Move is a programming language. It has a compiler. So it compiles to bytecode like many other languages, and we've designed a special bytecode that has some of the security features and the resource concept built into the definition of the bytecodes, which are executed by the virtual machine. So we do semantic checks on the bytecode, like many other systems, including Java, because we don't want to have to trust the compiler. So this removes the compiler from the trusted computing base. So the semantic checks include type checking, borrow checking, which is a little similar to Rust, etc. And that way we don't have to trust the compiler. We just have to trust the virtual machine and the smart contracts, the actual bytecodes. Okay, so to the topic of the talk, the Move prover. This is a formal verification system for these bytecode programs. So I've been working in formal verification for a long time, and like other people working in the area, after a while, particularly when you try to apply it practically, you discover there are many frustrations. So this is an interesting project because we're not starting with legacy programs. We're not trying to verify the Linux kernel or something, and we're not starting with legacy programming languages. So when the Move prover started, the Move programming language design was well underway. So we're not totally co-designing the language with the prover, but we are starting with a relatively clean slate where we can avoid some of the decisions that make formal verification difficult in other systems. So problems with traditional software are that developers don't want to write specifications. I'm not sure that all our developers want to write specifications too, but we don't have very many, and the prover team is as big as the team that's developing the software at this time. So the specifications are integral to the standard library modules. Programming languages tend to be too complex and ill-defined. Move doesn't have a formal specification at this time, but we have a pretty clear idea of the semantics of the language, and we will be developing all those things. Move is a relatively simple language, and it's restricted to what we need to do on the blockchain. Presumably over time it will become more complicated, but I'm hoping that the Move prover can track that as it evolves. Programs in general are too big and ugly to verify. People usually don't care that much about bugs. I mean, it's a sad truth. One of the things I learned was that with commercial programs that try to hunt for bugs in software and legacy software, one of the very biggest challenges is how to rank the bugs because people don't want to fix them all, right? So how do you list the most important bugs so that developers know which ones they need to spend time on? I want to avoid the situation, and we'd like really to fix all of the bugs in our system. So we're in a situation where we can do a certain amount of co-design of the verification tools, the programming style, and the verification methodology, and a little bit of the programming language as we go. And so I think in formal verification nirvana, that's what you would do. Verification is actually harder than most of the other things. It's harder than programming language development. It's harder than actually writing descriptions of systems. And I would love to see formal verification driving the design of everything else. We're not quite there at Novi, but we're in a much better situation than most people are. Okay, so let's get into more details about formal specification and verification of Move programs. So the Move prover is really a classical Floyd-Hoare approach with explicit specifications. So we're willing to take the time and put the effort into writing these specifications because the stakes are sufficiently high to warrant doing that. Our specifications are mathematically precise. They're written in a very standard, we've developed it ourselves, and it's not the same as everything else, but most of the features are pretty conventional. It's first order logic with types, basically. Specifications are separate from implementations. So we derive value from the fact that the specifications are independent of the code that was written. And so in practice, what happens, and what's happened ever since I started working in formal verification, is that when you write specifications and start verifying them, many of the problems are problems in the specification. And so some people just regard that as a tax that they have to pay. And but I regard it as a way of debugging the specifications because I consider the specifications to have value independent of the implementations. The specifications explicitly capture the intent of the, I should say developer rather than user. I'm thinking the user is the user of the prover, but the person who writes the Move code. And so formal verification proves that a Move program satisfies its specification and for all inputs in all states. And our goal is really the classical formal verification goal of proving correctness, not hunting for bugs. We assume we'll find bugs, and we found some already, but the goal at the end of the process is to have confidence that the code meets the specifications. Okay, so when I was thinking about this, before I actually took the job at Facebook, I said that specification may be the hardest problem. So we know that formal verification is hard. You run into scalability difficulties and software difficulties of every kind. It's a really challenging area, but the problems that I didn't know there are, good solutions or whatever, were really about how to do specifications so that we can count on the specifications being complete. And I won't claim that we solved that problem, but we at least recognize that it is a problem and we're working on it. So the goals of formal specification, well, the issue I'm most concerned about is errors in specifications. So you can get false positives, and in the conventional software world, the biggest problem with a tool is false positives because they waste developer time. For us, it's not our biggest concern. False positives are annoying and they require debugging and they waste some time, but they don't result in missing vulnerabilities in the software. False negatives are, to us, are more worrying because we want to prove that these systems are correct. We want to show that there are no major functional errors or security vulnerabilities, given the stakes. So it's important to us to enable users to write specifications in the most obviously correct form. So we don't want to require over-specification or under-specification. And I've stated what I call the principle of obviousness, which is we would like to be able to write specifications in a form that are as closely related as possible to the way that somebody is thinking about the end-to-end functional correctness of the system. So these are goals, they're aspirations, and we're working on achieving them, but I won't claim that we have achieved them. It's just what we're trying to do. So here's what our current system looks like. I won't go through it in full detail, but we're starting with a pretty standard language infrastructure. We translate into the Boogie tool that was developed by Microsoft. We have actually made some changes to the tool, and those are part of the open source system now. But the tool mainly does what we need to. We're using Z3 and sometimes CVC4 as the back end for Boogie. And then we put substantial work into developing comprehensible counterexamples when something fails, because it's very important to the productivity of people writing specifications and verifying them to be able to have a diagnosis when something doesn't work. That's an ongoing project. It's a continuing challenge. I think we've done a pretty good job of it considering the challenges, but there's still a ways to go. Okay, so if you're not familiar with Boogie, it's a very well-known tool, but it's a verification intermediate language between a source level program and an SMT solver to sort of bridge the gap between them. So it looks approximately like a simple imperative language. It has procedures, assignment, it has loops, it has data structures that are related to the things you do in SMT solvers. It likes maps. And then the problem we have is to translate a bytecode program to Boogie and verify it. Now, this has gone through many iterations. It's a non-trivial process, but I won't drag you through all of the improvements and mistakes and whatever that we've made in this process. It's also a continuing project. So our approach is to implement each bytecode as a procedure in Boogie, and then bytecode program turns into a sequence of procedure calls in Boogie. The specifications translate into Boogie code and Boogie pre and post conditions, mostly pre and post conditions for individual functions. So a lot of our work has gone into modeling memory. Now, this is the case in most verification systems for software. So Boogie code is imperative. It modifies a state. The state has a program counter, local parameters, and a global store, which is the blockchain state. And much of our thought and work so far has gone into finding the best way to represent the store. So that's important for correctness. It's also very important for the efficiency of the verification system. So in SMT-based software verification, getting your memory model right is typically a challenge. And so the move memory model, the language memory model, is novel. And we've tried to do translations that are fairly close to the semantics of the model that's in the language for a variety of reasons. So the move model, memory model, has this borrow checker, which statically ensures that there'll be no aliasing. So move has references, but it has, in a sense, copy semantics. It doesn't, you can't have the wild aliasing that you get in C and C++ and Java and other languages. So one of the first model we developed was a very conventional heap-based model for use in an SMT solver. And so we represented the heap as a collection of arrays, one for each different data type. So our references, which are kind of pointers, were represented as integers that index into the arrays, and the arrays were memories. Good, so there's a different array for each type. So the pointer is an integer, or the memory address is an integer, and there's a value stored in the array. And this worked okay, but it was not very efficient. Framing was particularly bad. You know, when you're verifying software, you have to say what doesn't change. And we had one giant data structure with all our states, so that was an annoying problem. Plus, the model was unnecessarily general for move. It could model many blockchain states that were completely impossible to reach using move programs. And the possibilities of aliasing in this model made for a big struggle when we had to run it through the SMT solver. So we moved to a tree-based model. And in fact, we've gone through several iterations of this tree-based model, the most recently being a few weeks ago. But at a high level, the idea is that the memory is addressed by paths. And so if you keep a mental picture of the tree I was showing you, there's an address, and then there's a type stored under the address, and then the type can have fields, and those fields can be structs that have other fields. And so a path is just the address of a location somewhere in that tree. And so the instructions in the bytecode program involve copying, moving, and deleting subtrees at various paths. You could also get references to subtrees and update mutable references, so you can replace subtrees with other subtrees. So we're working on another model that, and in fact, we've got one now that exploits the move copy semantics. So basically, we don't have to reason about aliasing so much. So this has been something, you know, Shaz Kadir has been really leading the development of new memory models, and it's an intellectually challenging area, but we think we're getting better and better. It's improving performance, and it's making some of the things we have to do in the verifier simpler with every iteration. Okay, so let's talk about specification a bit. What I said is the biggest challenge. So this is also something that's undergoing many iterations. And we find ourselves in a situation now where we're experimenting with specification style. So it's more important in the specification language at this time to go for flexibility and expressiveness, even if it's a little bit dangerous. And then as the specification style evolves and we're comfortable with writing specifications in certain ways, we'll probably change the language and maybe restrict it in some ways. Okay, so once again, what the tree looks like, we've got addresses at the top, and then we have a layer of types that are published at each address, and each type is a tree because it's a record with fields that can have records that have fields in them. So one of the things we need to be able to say and ask in the specification language is, does a resource exist at the top level? So you can publish types with addresses or not publish the types there. And so one of the things you want to say is, does this address have a Libra account.t at it? And so the way you write that is there's an exists, which is unrelated to logical exists. It's a little bit of a naming problem, but we can ask whether the type is published at an address, and you can see in the syntax that there's a place for the type and a place for the address. So that's a basic predicate in the system. You also may want to access data that's in the tree, obviously. And so the way we do that is if something does exist, we can reference the tree by saying global, giving the type, and the address, which gets us to the Libra account.t node, and then we can descend down the tree to find in the type with by listing fields. Hang on a second, I'm trying to block out noise. One of the disadvantages of COVID is that when you're working at home, all the construction projects of the neighbors' houses interfere with your talks. Anyway, I hope that's better. Good, and so I'm going to start with the simplest kinds of specifications. So in addition to all of this, it has the usual logical operators, right, that we're all familiar with, and arithmetic and all that kind of stuff. So the system is actually based on pre and post conditions. And so a simple function here might have, so this is very standard. It is a language we invented ourselves, but we borrowed a lot from other languages, including Boogie and Daphne and whatever. And so we have requires, which is a precondition. In this case, I say that what the code does is actually store a token at a particular, an info of a token at a particular address. It publishes it. And so before the code executes, that should not exist. Since these things should not already be published. Since these things are resources, it'll get a runtime error, overwrite existing data, because that would eliminate, that would involve losing the resource that you overwrote. So we say that a precondition here is that there isn't already an info token published at that particular address. And then after the code executes, it actually publishes the token, so the token actually exists. And then we may say that the total value initially is 0, and that there's some other field, which I'm not going to explain, called a pre-burn value that is 0. If you actually go look at the standard library contracts, there's something like this in there, but it's evolved significantly since I took this example for the talk. This used to be pretty much the exact code in the system, but it's evolved since then. So one of the features we have is this construct we call aborts if. So instead of runtime errors or exceptions, move programs abort. And the difference between a runtime error and an abort is that an abort cancels an entire transaction. So it goes back to the state before you started the transaction, even if you've done a series of function calls and the transaction are deeply nested in function calls. So the side effects do not persist if you abort. And so there are all sorts of conditions that cause abort, such as overflow, references to non-existent memory, etc. There's, if you do abort, it cancels everything, all the changes you may have tried to make during the transaction. And so there are no changes, except that a little bit of your, the money in your account is consumed to pay for the computation you wasted while you were aborting. Some programs are supposed to abort under certain conditions. So for these things, we do not want the verifier to just report the possible abort as an error. It's something that is supposed to happen under well-defined conditions. But if the abort is not expected, we do want it to be reported as an error. And so then what we need, or if an abort is supposed to occur and does not occur, that's also an error. So what we need is a way of specifying what the programmer's intent is with abort. And so the aborts if says, has a condition that comes after the keyword aborts if that says when an abort is supposed to occur. I'll mention that this is kind of an experimental feature, and we know that we need it some of the time, but even within the Move Prover team, there are differing opinions about the importance of having really detailed aborts if specifications. Post conditions assume that no abort has occurred. And so obviously, if you get to the end of the transaction, you didn't abort. And so any conditions that hold there can count on the fact that the abort conditions were never true. So if we do an ensures P, that gets translated to if it did not abort, then P holds. More interesting than the local specifications are what I call global specifications, but global specifications are actually built on a foundation of local specifications. So what we found is going into detail about pre and post and aborts if conditions tends to lead to missing the forest for the trees. Ultimately, we have requirements that come from business requirements or regulators, and they are typically about changes on the blockchain state that may occur with multiple transactions or calling multiple functions. So you can't just specify those with pre and post conditions. So the most important properties tend to be global, and so those involve multiple functions in a module, and may involve properties, they usually involve properties of the global state of the blockchain, and they may involve change over time. And so we have limited ways of reasoning about temporal properties, very, very limited ways. So for example, the most obvious example is invariance. So properties that are guaranteed by a module to be true for all time, such as that the sum of the currency is accurately represented by the variable that represents it. Another property that I found myself specifying is persistence. So once a property becomes true, it stays true forever. So let's look at an example. This is something you will see in several other blockchains as well. So as of the time I wrote this talk, and this has changed a little bit, but we still got it in there, there's a module called Libra.move that supports minting, burning, deposit, and withdrawal of multiple currencies. Each currency has to be registered, which initializes the currency. And for each currency, there's a variable called market cap with a field called total value, which tracks the total value of all the tokens of that currency. We want to show that this total value thing is actually equal to the true total value of all the tokens of that coin type that exist. So to do this, we use ghost variables and some other features. So we need to show that the market cap total value is correct. This is the total value thing is maintained in the move code. And what we're trying to do is show that that maintenance is correct. We need to compare it with another variable. So we come up with a ghost variable, which we call sum of token values, which is parameterized by the type of the token. And that's just an integer. So good. So token is the type parameter. So we represent each type of currency as a different type in the move module. So we have to update this ghost variable. And so what we do is we actually instrument the bytecode instructions that create and delete token objects to update this sum. And so what this says is every time you create, the pack is a create function here, is the create bytecode. Unpack is the destroy bytecode. And so every time you pack a new token, it adds the value to the ghost variable sum of token values. Every time you unpack a token, it subtracts the value from the sum of token values. So we're basing this on the bytecode, so the correctness does not depend on the source code or the compiler. We want to remove them from the trusted computing base. So we have another feature that's a bit dangerous, but I like it. It gives us flexibility to try different styles of specification called a schema. And so the idea with a schema is that you can take a programming pattern and apply it to a bunch of functions. And so lots of features can be implemented using schemas, including features we haven't thought of yet. So an example is a global invariant. So I'll simplify it with so this is the invariant we want to specify for the sum of tokens, that the sum of tokens, the ghost variable we're maintaining, is equal to the actual variable that is maintained by the move code. And so that's really just an abbreviation. And so it's an abbreviation for invariant P is an abbreviation for requires P and ensures P for every function in the module. And so the schema itself is like a function definition. It doesn't do anything by itself. It has no effect until it's applied. And what application does is automatically insert it into the specifications of a collection of functions. So in this case, what I said is take this schema and apply it to all of the functions that have a token type parameter. So basically what this does is take that invariant, split it into an requires and ensures, and then automatically add the requires and ensures to every function in the module, which is what you would do if you're trying to do the induction step of an invariant, prove the induction step. Okay. So that's how you do invariance using schemas. So we didn't have to implement a separate invariance feature. And then you can use schemas for other things. So for example, one of the properties I want to specify is that only minting and burning can change the total amount of currency. I don't want somebody to be able to counterfeit currency using some other function. And so I can write a schema saying that the total amount of currency does not change. And then I can apply that schema to everything except the mint and the burn functions. And so that says that every function that's written now that's not starting with the word mint or the word burn, and every function that somebody might write in the future, might add to the system, has to satisfy the property that doesn't change the total amount of currency. It can move coins around, but it can't create or delete or change the value of coins unless those functions happen to start with the word mint or burn. So they're clearly flagged as functions in the module that can change the total amount of currency. Another property that we can do with schemas is a persistence property. So if I want to say that once a currency is registered, it stays registered, I can write this function in the specification saying the token is registered, and then I can say if that's true in the previous state, it will continue to be true in the next state. And so that shows that implies that once this property becomes true, it remains true forever. And so without adding any features to the system, I can just define a schema that has this property, and then I can apply it to all of the functions in my module. So we also use schemas to reduce repetition, particularly in the boards if, because if we have conditions that are repeated frequently, then we can put them in a schema and just apply them to everything they apply to. Okay, I'm running a little bit over, so I will wrap up very quickly. I want to acknowledge that this is not the only project like this. I know of Verisol, Solci, Verified, SRI, and the company Certora, Muli Segiv's company. And I'm not entirely sure what Certora is doing, but I believe they're doing SMT-based verification of smart contracts. So these are all systems that work with smart contracts, and they're based on automated verification using SMT solvers. And the first two are based on Boogie. These are operating, so they're working on smart contracts in the blockchain. The major difference between those projects and these projects is that they're based on Solidity and Ethereum. So this is a legacy blockchain language, and it has a completely different set of challenges than Move. And in fact, formal verification is more important and probably harder for those systems because the language is very, very dangerous. Okay, there are many issues I haven't talked about. I won't go into detail, but I want to make the point that this is a real project trying to do real stuff, and you have to deal with a million issues, some of which are hard and some of which are interesting and some of which are not so interesting, but we're doing the real thing, and so we have all these problems. I'm not going to enumerate them. So to conclude, Move programs and smart contracts in general kind of hit the sweet spot for formal verification. So when you're choosing a formal verification problem, it's good to find something where the cost of bugs can be high. It'd be great if you're dealing with systems that are relatively simple, and the wonderful thing about smart contracts is they're pretty short compared with regular software. Starting with a clean slate makes the verification problem much easier. And the approach that we're using is a highly automated Floyd-Hoare-based style verifier. Move and the Libra blockchain create some unique issues and opportunities. Some of these we're still discovering, and I haven't talked about them all here. I've tried to mention a few of them. And our biggest worries are specification correctness, and as always with verification, how do you scale up to big things? With these combinatorial programs, you're all familiar with a case where the program just doesn't terminate or runs out of memory. And of course, we sometimes have those problems too. So please stay tuned for further developments. This project is evolving rapidly, and we'll have more to say later. I want to preview a tools presentation. We did get a tools paper accepted. And so after this talk, Emma Zhang of Novi, who's working on our team, will be doing a overview and a demo. So the tool paper goes into a little more detail. It focuses on pre and post conditions rather than the global properties, and just talks about things in more detail than some things than this talk. Okay, I'm sorry for going a few minutes over time. I guess I'm ready for questions.
Well, let's thank David for his wonderful session. We do a virtual round of applause. David, I can go on forever asking questions, but I know there are lots of questions on the Slack channel. So I'm going to start with just a comment and a question. Can you hear me okay?
I can.
Okay, so my comment is, so you mentioned the Verisol project. So we've been doing some work on verifying formal verification of Azure blockchain code. So interestingly, when we started out, we wanted to find bugs to formal verification. So the bugs were an outcome. But as we matured, I mean, we found that the outcomes are really the specifications. And they make a lot of sense in this domain because those are things that you can give for people to, so mutually distrusting parties can trust the specifications and not the code, which is just too clumsy. So I like that you echoed that in your presentation at some point. I think that's a great opportunity. The question the first question is essentially, have you explored, so in Verisol, we found that having some kind of bounded verification before we go to inductive proofs can be a very good way to get some bugs out, or even runtime verification. Have you thought about either of them in this context?
I thought about them a long time ago, but as we focused down on sort of getting things done in the short term, and so far, I guess we don't have particularly complex protocols in our standard lib. I looked at your at least one of your talks, and I'm familiar enough with some Solidity code to understand that sometimes they have some rather complex things you can model as state machines, right? And for something like that, you might really, maybe bounded verification would be more useful. So it might be useful in our case, but we've been able to specify the inductive invariance that we need to do so far.
Great. So I'm going to take questions from Slack, and there are lots of them, so I'm trying to group some of them. So there is a thread of questions that Ishil, Rupsha, and Dave asks, which is, how do you have you thoughts about, what are your thoughts about going beyond the pre-post conditions and module invariants in terms of liveness, relational properties, and security properties like privacy?
Our thoughts are limited. So we do end up specifying a lot about access control using the simple global properties I talked about, where we apply a schema to a bunch of different functions. So we have a lot of properties of the form. Nobody can change the state in a particular way except the following account under the following conditions. For example, so privacy, we have almost nothing to say about. In fact, we've got a public blockchain. So, you know, we have run into a few problems with cryptography where we're using basically a Dolev-Yao model. So we have functions with inverses and that sort of thing. So we haven't really dug into those deeper issues, and so far, you know, just doing the basics has been quite a challenge.
So there's another thread of questions, not about the move programs, but the underlying protocol in the VM. This is by Kedar, Stephen, and I believe someone else. So the questions are about, do you have proof of work in Libra, and do you have specifications for VM or the protocols underlying move? The blockchain
We don't have proof of work. So this is really a Byzantine consensus algorithm, and that was done. So it has been formalized and proved in CAV by another person who works with us. So I believe that's published, and you know, I actually haven't looked at it carefully. For the VM, we haven't formalized it as much as we really should, just because of lack of resources. So there's an informal specification, but it's obviously part of the trusted computing base of this system, and we'd like to be able to go over it more thoroughly than we have so far. It's written in Rust. Most of the system is written in Rust, and with this thin layer of smart contracts written in Move.
There is another question. I'm going to roll two questions. So there is a question about what do you, Ishil asks, what do you do about the brittleness of SMT solvers? And there is also a question about Are there bytecode level specifications? How are they generated from Shaukai? So kind of two different questions, but
what was I missed? I didn't understand the last two words of the last sentence.
the last two words were, are there bytecode level specifications and how are they generated?
In a sense, everything is a bytecode level specification. We annotate the source code with specifications, but the verification is actually done on the bytecode. The bytecode is sufficiently high level that we can talk in terms of types and arithmetic operators and that sort of things, and it all makes sense. And can we please mention the first question again?
The first question was essentially, how do you deal with the brittleness of SMT solvers?
We suffer, right? So, you know, one of the real frustrations with SMT solvers is not simply that they go into apparent infinite loops every once in a while, but that it's hard to figure out what's going on. Back when I was making SMT solvers, you know, I could interrupt something that was running at length and print out some data structures and figure out what's going on. But I think one of the impediments to this field is that we have kind of two communities, right? We have people who use SMT solvers and people who work on SMT solvers, and they're often not the same people. And I think that division has meant that the people who use SMT solvers treat them as black boxes, and they don't have the knowledge or patience to go inside and fix stuff. The people who are actually working on the SMT solvers don't have a visceral appreciation for the problems they cause at the application level, or may not know the specifics of where they're failing. And so one of the things we are doing on my team is trying to bridge that gap a little bit. We don't have SMT expertise other than my historical expertise in the subject on the team, but we're collaborating with Clark Barrett and the University of Iowa. And you know, one of the best things you can do if you're on the application side is give your troublesome examples to the SMT researchers, and then out of professional pride, they will try to make their solvers work better. They'll tune them to your application. So, you know, we go through a series of panics where, oh, something's not finishing in time, and then we try to find optimizations. And a lot of the optimizations we've been doing so far are trying to limit the number of formulas that the SMT solver has to look at by various means. But it's an ongoing battle.
There is another thread of questions around specifications. So Akash asked, who are writing the specs? Are these specs for a particular move program or specs for the system? And there is another question by Amir Mohammed saying, how do you make sure the specifications are correct?
So for the first question, we are focusing not so much on delivering a functional tool as delivering a tool we can use internally by experts to verify the standard library. So for the first iteration, Libra is going to be a relatively closed system with a standard library and a set of canned transactions. And so the people writing the specifications include most of the Move Prover team, because we want the people who are developing the tools to also be using the tools, writing the specifications, and some of the people who are writing Move programs. I guess my working memory is only sufficient to remember one question at a time. So what was the second question?
The other question, how do you check your specifications are correct?
Well, I mean, that's a very difficult problem. So the first thing that every verification person does is just use them to verify stuff, and you discover a lot of errors in the specifications. But my biggest concern is about gaps in the specifications. And so we're doing some research this summer with an intern, exploratory thing. You know, there are simple things you can do. If at any point you can prove false, you know you have trouble. You know you have trouble. And so we're looking at some other things, like whether sub-expressions of specifications are constant, so are they always false or always true, which is often a sign that, you know, you have to wonder why somebody wrote a specification of the form P implies Q when P is always false, right? And perhaps we can check for coverage of specifications by some kind of mutation coverage metric, but we haven't implemented the mutation coverage. We're just experimenting with some of the other things over the summer, and maybe those will evolve into things we incorporate into the tool.
In a similar vein, there is a question from Ian asking, how do you distinguish abort if statements which are unexpected from those that are?
We have to do it. I mean, we're wrestling with this problem right now. There are a bunch of problems with the board CIF, including the fact that they become very, very detailed, the specifications. So we're going to have to do it by a combination of programming convention and a little bit more language support. And then that also affects how we write the specifications and how we report them. So I think Move programmers will have to become more disciplined about using explicit insertions to do aborts versus just letting certain instructions crash, so that we know that if it wasn't an explicit assertion, then it's an unintended, it's either a user error or some kind of system error. But we're still trying to nail down exactly what we want to do there. It's a very good question.
There's a question about schemas. So by the way, schemas reminded me of something that we did in this Havoc project for instrumenting specifications on a large scale using strings. So that seemed very natural and I like it. So the question about schemas is that you talked about schemas being matched against method names. Did you consider user-defined function annotations as an alternative?
What do you mean by user-defined function annotations?
I do not know.
So we have specification functions that we can use. The problem is that if you want to use ensures or requires, that is not part of a logical, that's not part of the logic, right? That's a command or something. So the schemas allow us to substitute ensures and requires automatically or introduce them in specifications of functions. With the schemas, we also have logical transformations you can do on them, because we discovered sometimes if you have a function that does some operations and then does an assert, for example, you may have to add basically if and else's or implications to qualify the assert failure. And so we found it useful to be able to do that with schemas to some extent. So you can do logical operations on schemas in a way that may or may not, evolve in this system.
So that was a question from Scott. There's another question from Alexandra asking, have you explored separation logic, which is close to Move's linear types and supported by tools like Viper with a VI, PER?
No. Working at Facebook, there are people who are experts on separation logic who keep advocating it, but we haven't seen how directly helps us yet. So I suspect as we look more and more at framing problems, we'll get closer and closer to separation logic. But yeah, turning it into a concrete proposal has been a bit difficult.
Okay. Well, I have one final question on schema. For the schemas, can you allow the state change operations? Can you introduce state change or only ghost variables? Okay.
We can, a principle of our specifications is that they don't affect the execution of programs at all. Okay. With ghost variables, you can update them. And I gave an example where those are updated by particular bytecode instructions. We'll probably be expanding the ghost variable feature so that they can be, what people typically do with ghost variables is that they annotate programs with additional code that manipulate the ghost variables. They make sure that the ghost variables can't affect the behavior of the program. So we'll probably end up doing that soon.
Okay, I have to take this question from Alan. He'll be angry at me. So he's saying there's a lot of interest in verifying smart contracts. Is that the software, its software is in the Goldilocks zone, relatively simple, high value? Have you noticed anything idiomatic about smart contracts that might lead to more specialized verification techniques?
I think we're getting inklings of it, but at this point, I must say that I think I'm 10% of the way into really understanding this problem. So we've actually been building the system at a high rate of speed for about 7 months. We spent a year doing prototypes and things, and I think we're only barely beginning to understand the problem. And to do that at scale, you just have to spend a lot of time writing specifications and working with real Move code. And so the things that are most that are most novel in our system, I think, aborts if is something that lots of smart contract specification languages will have in one form or another. I think the reasoning about resources is interesting, and we have a number of problems there that we haven't fully solved. And I'm not sure that I can say anything coherent about them, but we're definitely facing some novel issues just because of the design of the move language.
Okay, I think we have to wrap up because the next session starts in 10 minutes. So let's all thank David. It's been a pleasure to have you. Thank you all.
So I'll promise to go back and look at Slack and try to answer the questions that
yes.
we weren't able to do. Not sure when I'll do that, but maybe later today.
And for everybody else, there's the next session, 9:15 to 10:45, and we have the breakout session at 10:45. Please come and join. If you're new to CAV, it's a wonderful opportunity for social interaction. With that, we conclude this session. Thank you. Bye.
Thank you.